Hi there, in this video I want to go through the derivatives of trigonometric functions. So let me just title this derivatives of trigonometric functions. Okay, so let me take a red pen and a ruler. Underline this. So let me go through the standard derivatives firstly. So and let me number them also. So number one, if y equals sine x dy over dx, so when you differentiate sine you're going to have cos x. Okay. Number two, y is equal to cos x dy over dx. When you differentiate cos you get minus sine, so it's minus sine x. Number three, y is equal to tan x dy over dx in this instant is sec squared x. Okay, so these are the derivatives of sine, cos and tan. So let me continue over here. So number four, if you differentiate y is equal to cosec x dy over dx, so when you differentiate cosec you get minus cosec x cot x. Okay. Number five, y is equal to sec x. When you differentiate sec x, dy over dx is sec x tan x. And number six, y is equal to cot x. When you differentiate cot x, dy over dx is minus cosec squared x. Okay, so these are the derivatives, the standard results for sine x, cos x and tan x, as well as cosec x, sec x and cot x. The way that you could learn this is, so one way is, whenever you differentiate a ratio starting with c, so ratios starting with c are cos, cosec and cot, the result will have a negative in front. So for example, if you differentiate y equals cos x, it starts with a c, expect the result to be negative, so it's minus sine in this case. If you differentiate cosec, again that ratio starts with a c, the result will have a negative sign in front. Okay. However, these are the standard results for the derivatives of trigonometric functions. Okay, the 6 basic trigonometric functions. Now further to that, let me continue. So let me give you some additional results based on these results. So let me title this additional results. Let me underline this. So based on these results, number one, y is equal to a sine ux. So a is a constant, so the term in front of the function sine is a constant, so a is a constant. Ux is a function of x, so where a is a constant and ux is a function of x. Okay, and in order to calculate its derivative we need to use a chain rule. Okay, so let me go over the result using a chain rule. So remember the chain rule. So by the chain rule states that to calculate dy over dx, the gradient function, first you need to calculate dy by du and then multiply by du by dx. So that was the chain rule. Okay, so in this case let's apply the chain rule in this instant. Y equals a sine ux, a is a constant, ux is a function of x. So let me continue on the reverse. So I'll call this step number 1. And step number 2, let's work out dy by du using y equals a sine ux. So here's step number 2. So y is a sine ux, but I'm going to write it as a sine u, so my u is the shorthand for ux, okay? So when I calculate dy by du, so when I differentiate this term with respect to u, remember when you differentiate sine, it's cos, so you're going to get therefore a cos u. So bearing in mind a is a constant, so if you differentiate with respect to u, derivative of sine is cos a cos u, okay? So in a final step, I'll call that step number 3. So in the final step, let me replace the dy by du in the chain rule by the result that we've achieved in step 2, okay? So therefore, dy over dx is equal to dy by du, so dy by du is a cos u, multiplied by, so going back to the chain rule, multiplied by du over dx. So multiplied by du over dx. Okay? So this is the result that you'll get for the derivative when you differentiate a function of the type a sine ux. A is a constant, remember, so this result only works where a is a constant, ux is a function of x, okay? So let me go through another result, number 2, supposing y equals a cos ux. So again, a is a constant, ux is a function of x. So let's use the chain rule again. Let's come up with the result for the derivative. So in step number 1, let's apply the chain rule. So by chain rule, dy over dx, that is dy over du times du over dx. And remember step 2 is to work out dy by du. So this is what I did earlier. So based on our equation here, y is a cos ux, and bearing in mind a is a constant, u is a function of x, dy over du. So if I differentiate with respect to u, derivative of cos is minus sine, so it's minus a sine ux, okay, or minus a sine u. Remember, u is the shorthand for ux, okay? So if I replace, in step number 3, if I replace dy by du in my chain rule, therefore dy by dx will be dy by du, which is minus a sine ux, or minus a sine u, multiplied by du over dx. So this is the result for when you differentiate y equals a cos ux. A is a constant, remember, ux is a function of x. So this result is only true if a is a constant, okay? I'm not going to go through the other results, but the remaining results follow the same approach. So let me continue over here. So let me call this result number 3. So if y equals a tan ux, dy over dx will be a sec squared ux, okay, multiplied by du over dx. So that's result 3. So result 4, again based on the standard derivatives and based on the chain rule, if y is equal to a cosec ux, dy over dx, so according to the chain rule, it will be minus a cosec ux cot ux times du over dx. So once again, you can prove these results using the same 3 steps that I've highlighted earlier. Okay. Let me continue. Number 5, y is equal to a sec ux dy over dx will be a sec ux tan ux times du over dx. And last but not least, number 6, y is equal to a cot ux dy over dx, the derivative, so that should be minus a cosec squared ux times du over dx. Okay, so here are the remaining results, and let me stress that these results are only applied if a is a constant. Okay, so you only apply these results if a is a constant, ux is a function of x. If a is not a constant, we may need to use, or we'll probably use most likely, the product or the quotient rule. Okay, so if a is a constant, we're going to apply the chain rule related results. However, if a is not a constant, so if a is a function of x, we may need to use, or will probably most likely be using, the product or the quotient rule. Okay, so please bear that in mind. So let's try some examples. So let's try some examples on the reverse. Example number 1. Okay, so let me find my red pen and a ruler, and let's try example 1. Here it is. So example number 1, the question is to find dy over dx, and in part A we're going to differentiate y is equal to 2 sine 2x squared plus 1. So 2 sine 2x squared plus 1. So sine 2x squared plus 1 is one function. Okay, now what I normally do is I say to myself, right, I look at the term in front of my function. So the term in front of my function is 2. Okay, 2 is a constant, so that means I can use my chain rule related result. Okay, so remember that term we regarded as a when it came to the results. So let's remind ourselves, if y equals a sine ux, remember, we derived the result, and that result was a cos u times du over dx. But in our function in question, a, the term in front, is 2. So 2 is a constant, a is a constant. We need to use the chain rule related result as I've shown earlier. So dy over dx, so let's work out that. Now what I would say is you don't need to memorize the result. Okay, I always advise try not to memorize so many formulas or so many formulae. Okay, understand what the result is trying to say. So when it comes to that result that I was showing earlier, so if y equals a sine ux, remember dy over dx is a cos ux times du over dx. So the result is trying to say we just differentiate the function using our standard derivative. So when you differentiate sine, we know it's a cos, so it's an a cos ux, and then we always multiply by d by dx of the term. Okay, the term meaning the angle. Okay, so when you differentiate in particular using the trigonometric chain rule related result, provided that a is a constant, differentiate your ratio. So when you differentiate, sine is a cos, so a cos ux, but multiply by dx of ux, which is the angle. Okay, so let's apply that approach here. So when I differentiate 2 sine 2x squared plus 1, 2 is a constant. When I differentiate sine, it's a cos, so 2 cos 2x squared plus 1. But we always multiply by dx of the angle. So ux is the angle, so ux is 2x squared plus 1. Okay? So now it's a matter of simplifying. Dx of 2x squared plus 1 is 4x. So if I continue, dy over dx will be 4x times 2, 8x, cos 2x squared plus 1. So that should be the final answer to part A. Okay? So remember, if A is a constant, use the chain rule related result. Try not to memorize the result. Work along the lines as I explained. So just differentiate your function using the standard result, but you always multiply by the derivative of ux, and ux for trigonometric functions is the angle. Okay, let's try another one, part B. So using this same approach, let's think about the method for this one. Y is equal to, okay, y is equal to 3 tan 3x cubed. So 3 tan 3x cubed. Okay, so let's think about this. The term in front of the function is 3. So that is our A. A is a constant, so I can use the chain rule related approach. So dy over dx. When I differentiate tan, the standard result is sec squared. So it's a 3 sec squared 3x cubed. But we always multiply by d by dx of ux, and ux for trigonometrics is the angle, 3x cubed. Okay? So now it's about simplifying. So when I differentiate 3x cubed, it's 9x squared. So if I simplify, dy over dx will be 9 times 3, 27, with this x squared, sec squared 3x cubed. So that should be the final answer to that one. Okay? Let's try another one. Y is equal to, how about y is equal to 2x, okay? So 2x cos 3x. So y is equal to 2x cos 3x. So let's think about this one. The term in front of the function, okay, is 2x. So the term in front of cos is 2x. So that term is not a constant. 2x is not a constant. 2x is a function of x, so we need to use the product rule in this case. Okay? So I'm going to take my u to be that term 2x. I'm going to take my v to be cos 3x. Okay? So going back quickly, the term in front of the function is a function of x, so it's 2x. 2x is not a constant, it's got to be product rule. Okay, so if the term in front of your function is not a constant, it's either product, or you can use quotient rule if you have a quotient of functions. Okay, so let's remind ourselves of product rules. So I explained product and quotient in previous videos. Okay, so in this case, step number 1, let's state the product rule. So by product rule, so remember the rule, dy by dx is v du over dx plus u dv over dx. Okay, so that's the product rule. Step number 2, I like to do a side calculation, and I'm going to do a side calculation calculating du over dx as well as dv over dx. So u is 2x, du over dx, when I differentiate 2x, simply 2. Let me do another side calculation alongside this one. V is cos 3x. That would make dv over dx. So once again, think about it. The term in front of my function cos is a constant. So let me circle that term. It's constant, it's 1. Okay, so that's the term in front of cos. So it's a constant, it's 1. That means we can use our chain rule related approach. So remember the idea, when I differentiate cos, it's minus sign. So it's a minus sign 3x, but we multiply by d by dx of ux, which is the angle 3x. Okay, so if I simplify further, d by dx of 3x is 3. So that would make dv over dx 3 times this minus in front, minus 3 sine 3x. Okay? So there are the side calculations in step 2, and in the next stage, final step, step 3, let's substitute these results that we found in the side calculations into our product rule. Okay? So dy over dx is equal to v in this case, so v is cos 3x, so let's write down that, cos 3x, times du over dx, so du over dx is simply 2, plus u in this case, so u we've chosen to be 2x, so 2x, multiplied by dv over dx, and dv over dx is minus 3 sine 3x. So minus 3 sine 3x. Okay. So let me expand the brackets. So when we expand, 2 times cos 3x, 2 cos 3x, and minus 3 times 2x is minus 6x sine 3x. And if you wanted to, you can take a common factor. So if I take a common factor of 2, okay, I'm going to be left with cos 3x minus 3x sine 3x. So that is the final answer to that part C. Okay. Right, let's try another one. So let's try another problem. So part D. So y is equal to, and let's differentiate 1 plus sine x to the power 3. Okay, so y is equal to 1 plus sine x to the power 3. Now, to differentiate this function, remember one of the rules that I've explained in the function of a function rule video. So if you haven't watched that video, here's the result from that video. So remember the result. So if y is equal to a ux to the power of n, and when you differentiate such a function, dy over dx is na ux to the power of n minus 1 multiplied by d by dx of the u term. Okay, so remember what I said. I've said in that video whilst doing examples, don't memorize the result, just learn what the result is trying to say. So the result is trying to say multiply by the power, take away 1 from the power, so that comes from normal differentiation, and then we multiply, don't forget, by the derivative of the u term. Okay, so back to the example. Now over here, our a term, so the term in front, so let me take a red pen, is 1. Okay, so that's the term in front of this function. 1 plus sine x, that is regarded as our ux or our u term. And the power 3 is our n term. So we can use that very rule that we've seen to differentiate this term. So dy over dx. So remember the idea. First we multiply by the power. So let me take that red pen. So if we multiply by the power, 3 times the 1 in front is 3 into 1 plus sine x. And don't forget, we need to subtract 1 from the power. So it's 3 minus the 1. Okay? And we also need to multiply by d by dx of the u term, and our u term is 1 plus sine x. Okay? So what needs to be done now is just to tidy this up. So d by dx of 1 plus sine x. So when we differentiate such a term, we're going to have cos x. Okay? So when you differentiate 1, that is 0. When you differentiate sine x, that's a standard result. You should get cos x. So therefore, dy by dx, that's going to be 3 into cos x multiplied by the 1 plus sine x, and 3 minus the 1 is 2. So that should be the solution to this problem. Okay? So that completes this example, and that completes the examples for this video. I hope you enjoyed this video, and if you did enjoy this video, a like will be very much appreciated. Do practice related problems, and I hope to see you soon. Thank you.